Let's talk about a manufacturing process that honestly sounds like it's straight out of science fiction. But here's the thing, it's very real and it's already building the future of high performance parts. It's called liquid molding, and it's completely changing how we make everything from supercars to spaceships.
So just look at a complex, modern part, like a piece of an aircraft fuselage. It has to be unbelievably strong, it has to be crazy light, and it has to be shaped with absolute pinpoint precision. But the real question, the real puzzle is, how on earth do you build that in one single piece?
Well, the answer is liquid molding. And when you boil it down, the concept is actually beautiful in its simplicity. You start with this engineered skeleton made of fiber. You inject it with a liquid polymer, a resin, and what comes out is a single, super strong, perfectly integrated part. It's a totally different way of thinking about how to build stuff. Okay, so let's start with its biggest, most game-changing benefit. Section 1, making the impossible possible. This right here is one of the biggest deals in engineering. It's called part count reduction. Just imagine replacing dozens or sometimes even hundreds of little individual metal parts, each one needing to be fastened or welded or bonded together with just one single seamless structure. I mean, this doesn't just make assembly easier, it massively cuts down on weight and, gets rid of all those little joints that could potentially fail. So that's the why. But how does it actually work? Let's get into section 2 and break down the recipe for making one of these perfect parts, focusing on the most popular technique. The method you'll hear about most is Resin Transfer Molding, or RTM for short. The secret sauce here is its matched two-sided mold. Seriously, think of it like a super high-tech, high-pressure waffle iron. This is what allows for those incredibly precise shapes and what the industry calls a Class A finish, which basically means it's perfectly smooth and ready to go, right out of the mold, on both sides of the part. That's key. And here's the whole process in 5 basic steps. First, you make what's called a dry fiber preform. We'll get to what that is in a second. Next, you stick that preform into the closed mold. Step 3, you pump in the liquid resin under pressure. Fourth, you cook it with heat to cure it. And finally, pop it out. You've got a finished rock-solid part. Sounds simple, right? But the execution has to be incredibly precise. Now look, RTM is powerful, but it's not the perfect solution for absolutely everything. The upsides are obvious. You get unbelievable precision, that gorgeous finish on both sides, and a ton of design freedom. But what's the trade-off? Well, those initial tooling costs are high. That super precise matched mold is a serious investment. So you might be wondering, with that big price tag, when does it actually make financial sense? This number right here is the key. RTM really hits its sweet spot for production runs somewhere between 100 and about 5,000 parts. It's the perfect bridge technology, way more efficient than making one-off prototypes by hand, but not as crazy expensive as setting up for, true mass production of millions of parts. Okay, so we've talked about the mold and the resin, the liquid plastic. But what about the skeleton that gives the part all of its incredible strength? Let's dive into that in section 3, the architectural fiber skeleton. This is the preform. It's the dry fiber architecture of the part, and it's meticulously engineered to provide all the strength and all the structure. I absolutely love this analogy from the source material. Think of the fiber preform as the steel rebar and the resin as the concrete you pour around it. Without that engineered skeleton, all you've got is just a puddle of plastic. The simplest preforms are just 2D weaves. These are basically layers of woven fabric, and they're perfect for creating strong, relatively flat surfaces, like the skin of an aircraft wing, where you need a ton of strength in 2 directions. But what if your part isn't flat? Well, this is where things get really clever. With 3D weaves and braids, you can create these incredibly intricate, integrated structures where the fibers run not just left and right and up and down, but forwards and backwards too, in the X, Y, and Z directions. They're designed to handle complex forces from literally any angle, which is how you can make things like structural I-beams or complex fittings all in one go. And this quote just nails it. For a long time, one of the big limits of composites was that they were great at handling forces in simple, flat planes. But as the source explains, these new 3D textiles are completely tearing down that barrier. This is exactly how these advanced skeletons are letting composites replace metals in some of the most demanding jobs out there. So we've got a pretty good handle on RTM, but it's not the only game in town when it comes to liquid molding. So for section 4, let's look at how different kinds of molds lead to different methods. This table does a fantastic job of laying out the key differences. On the left, you've got your traditional RTM, expensive, two-sided mold, high applied pressure. But on the right, you have something called vacuum-assisted RTM, or VARTM. And what's so interesting here is that VARTM uses a much cheaper, single-sided mold. It doesn't push the resin in, it just uses a vacuum to suck the resin through the preform. And that one change has huge implications for cost and scale.
And because the VARTM tooling is so much cheaper and you aren't limited by the size of a giant heavy press, it's the perfect method for making absolutely enormous parts. I'm talking about things like giant wind turbine blades or even entire boat hulls, all made in one single shot. It's pretty amazing.
Okay, so we've covered the process, the skeleton, the different variations. So what does this all add up to? Let's bring it all together in our final section, why this changes everything. When you put it all together, liquid molding really gives you 4 game-changing advantages. You get these integral structures, which get rid of weak joints. You get that massive part count reduction, which makes assembly simpler and cheaper. You give designers this incredible flexibility to create shapes that just weren't possible before. And the end result of all that, it's just superior performance. Products that are stronger, lighter, and way more durable than we could ever make before. This technology really is a glimpse into the future of how we make things. By combining these architectural fiber skeletons with liquid resin, we can now build things that, not too long ago, were considered flat-out impossible. And that leaves us with one final, really exciting question. With this kind of power, what are we going to build next?